Okay, so this will be the last time we meet. What we'll do today is talk about probability, which I think builds nicely upon the stuff that we've seen so far in the class. But before we start talking about that, a couple of announcements. So the grading breakdown will be released tomorrow. We're almost done grading the quizzes, and so tomorrow, hopefully, but worst case Saturday, you'll receive an email saying whether or not you've already passed the class and whether or not you need the extra credit assignment to pass. And so there's two cases there. So either you don't have enough points, have the points, or you have more than 3 unexcused. Okay, so if you fall into one of those two cases, you'll receive an email saying you have to do the extra credit assignment in order to pass the class. Okay, and the extra credit assignment will be, I believe, worth less than a quiz is worth for sure. I think it might be one or two, the weight of 1 or 2 homeworks. So you still need to get those points to get over the 65 threshold. Okay, but more details will come when it's released. And the extra credit assignment, the details will come out with the grading breakdown. It'll be due the Friday of Dead Week. Okay, and again, it'll be like a homework, but all of the questions will be graded on correctness rather than just completion. Any questions with that? Okay. Also, the feedback form that I sent out, I believe, over the weekend or Monday is due today. And the reason for that is I can't have the feedback form open while you have your final grades. So the feedback's due today, then you get your final grades tomorrow. Does that sort of make sense? So please fill it out if you get a chance. It's not too long. The link is on Piazza. I'd really appreciate it. Sounds good? Cool. So, today we'll start talking about probability, and a lot of this will be presented in a way that extends on the things you've seen so far in this class. Okay, so you'll see a lot of natural extensions between things we just did, especially towards the end of the semester, into probability. Okay? And so, let's get into it. Okay? Suppose omega represents our event space. Okay, this symbol over here is called omega. And suppose omega is the set of all possible outcomes of some event. Okay? So for example, probably the most common example of an omega could be all possible rolls of a dice. Okay? So if we're talking about the rolls on a dice, we could say omega is 1, 2, 3, 4, 5, or 6. We're talking about the rolls of a dice. Okay? So that's for a dice. If we're instead looking at all possible cards you can draw from a deck of 52 cards, omega would be all of the cards that you could draw. So for example, like a 2 of hearts, 3 of diamonds, blah, blah, blah. Okay? So the things in omega don't necessarily have to be numbers. They're just whatever outcomes we have. Is that okay? And now suppose A and B are subsets of omega. Okay, so for example, if we're talking about the dice, A could represent the set of outcomes of rolling an even number, and B could represent the set of outcomes when you roll a 4 or greater, for example. Okay, so A and B don't have to necessarily be single outcomes, they're sets of outcomes. Is that okay? So for example, A could be the set of options when you roll an even number, so 2, 4, and 6. And B could be you roll 4, 5, or 6. Okay? And so these are the 3, what we called axioms, which you can think of as being propositions that we assume to be true. They're like the ground truth, and everything is based upon this. Is that okay? We're assuming this is true. Everything we do in probability will be some sort of extension from this. Okay? So the first axiom is that probability is non-negative. Okay? So what that means is for any event, the probability is greater than or equal to 0. Okay? For any subset A of omega. Also what we say is that the probability of omega itself, which is the sum of the probabilities of all of the outcomes in omega, is exactly 1. Something in omega will happen. Is that clear? So for example, if you roll a dice, you will see one of the numbers 1, 2, 3, 4, 5, or 6. Right? You flip a coin, you will see either heads or tails. The outcomes themselves could have different probabilities, but one of them will happen, if that's the event you're looking at. Is that okay? And lastly, we say if A and B are disjoint, then the probability of A or B happening is the probability of A happening plus the probability of B happening. Okay? How is this similar to something we've seen before? Well, we saw before that if A and B are disjoint, the cardinality of their union is the sum of their individual cardinalities when they're disjoint, right? So if and only if A and B are disjoint. And can someone remind me, what does it mean for A and B to be disjoint? Their intersection is empty, right? Yeah. Sorry, I sort of said the answer before. Okay. So their intersection is empty. What are we doing here? Intersect B, not the set 0, but it's the empty set. Okay? Equivalently, the cardinality of their intersection is 0. Okay? And so for now, the most elementary definition of the probability of some set of outcomes is the cardinality of the subset divided by the cardinality of omega. Okay? So for example, the probability of rolling a 4 or greater is just, so for example, the probability of B, where B is up here, is just the cardinality of 4, 5, and 6 divided by the cardinality of 1, 2, 3, 4, 5, 6. Okay, which is just 3 over 6, which is a half. Makes sense, right? So it's a ratio of cardinalities. Sounds good? Okay, so you see how all of this sort of ties into the stuff we talked about at the beginning of the semester. And so here are a couple other further definitions that will be useful in some of the examples we're about to look at. So we say two events are mutually exclusive, and so that's an important term you'll want to know. Mutually exclusive, if and only if the probability of their intersection is 0. So mutually exclusive just means disjoint. Okay? And so what's an example of two events that are mutually exclusive? Well, so for example, suppose A is the event that the card I draw is black, and assuming I'm only drawing one card, and B is the event that the card I draw is red. Those outcomes are mutually exclusive. They can't both happen at the same time. If I'm drawing a single card, either it's black or it's red. It cannot be both. So we'd say those outcomes are mutually exclusive. But for example, the outcomes of drawing a card that's black and a card that's a queen, those could both happen when I draw a single card. So we would say those outcomes are not mutually exclusive. Okay, so their probability greater than 0. Sounds good? Okay. And then also, we say two events are independent if and only if the probability of their intersection is the product of their individual probabilities. Okay? So two events are independent if and only if probability of their intersection is the product of their individual probabilities. So my question to you is it possible for two non-zero events, so events that have probabilities that are not equal to 0, to be both mutually exclusive and independent? Is it possible for two events that both have non-zero probability to both be independent and mutually exclusive? Is that possible? Any ideas? Yeah. Exactly. Exactly. So, assuming that both A and B are in omega. Yeah, it's not possible. Okay? So, the condition for them to be being independent is that their intersection is their product. And the condition for mutual exclusiveness is that their intersection is 0. So if both of these conditions hold, then we must have the product is 0 But if the product is 0, one of them has to be 0. Okay? So it's not possible that two events with non-zero probability are both mutually exclusive and independent, assuming that they're both subsets of the same event space. Okay, if they're not subsets of the same event space, it doesn't really make sense to compare them. Okay, another question that has appeared in exams of courses that you might take in the future is it possible for an event to be independent to itself? Okay, and in what cases could an event be independent to itself? And so that's something you can ponder. But it's the answer is somewhere on this slide, is what I'll say. Okay, so any questions with these definitions? Okay, and so we're just laying down the foundations, but we'll look at some pretty cool applications in just a second. So, the first thing that's important to note with probability is that at its core, it's really just a ratio of two cardinalities. Okay? But both of those cardinalities are things we've learned to count when we talked about counting. Right? So before, a question that I could have asked you, and I believe this was on the homework, was how many ways can we arrange the characters in Berkeley such that Berk appears as a substring? Right, we did this before, and how we did it was we said, let's just block together the characters B, E, R, K. Then we have an E, an L, an E, and a Y. And then now how many unique blocks, or how many blocks in total do we have? 1, 2, 3, 4, 5. Divided by the repeats for the E's. Right, so I have 2 factorial. So that's the total number of ways I can arrange the characters in Berkeley such that Berk appears as a substring. Is that clear? So now, a question I could ask that's very similar is what's the probability that a random permutation of Berkeley contains Berk as a substring? And so, it's just a probability I found in the first part divided by the total number of permutations of Berkeley. Is that clear? So what I can do is find the total permutations of Berkeley. That would be B, E, R, K, E, L, E, Y. So how many characters do we have now? 1, 2, 3, 4, 5, 6, 7, 8. So 8 factorial divided by the repeats for the E's. So 1, 2, 3. And so now it's the ratio of the ones we want. So the cardinality of the set of outcomes where Berk appears as a substring, which is just 5 factorial over 2 factorial, divided by the total number of outcomes. So all the events. And in this case, the events are just the permutations of Berkeley. So 8 factorial over 3 factorial. And that's our probability. Sounds good? Another question I could ask is, what's the probability that a random permutation of Berkeley does not contain Berk as a substring? Well, so first, I want to find the numerator. Right? The numerator is just the total number of permutations minus the ones with Berk as a substring. Right? So the probability of not will just be the total minus number of ways to have Berk over the total. Is that clear? But this just reduces to 1 minus the probability of Berk. Because the total on the numerator and denominator both cancel out. So this pattern, 1 minus, you'll see very often when you get to probability. Okay? And so it's a pretty important thing to note. Suppose A is some event. The probability of A's complement, so the probability of not A, is 1 minus the probability of A. Is that clear? So another way to think of this is either A will happen or it will not happen. Okay, whatever our event is, either it'll happen or it won't. So the sum of those two probabilities is 1. Why can we just add them? Well, they're disjoint, right? A cannot both happen and not happen at the same time. Right? So for example, I flip a coin, either it landed heads or it didn't land heads. Those are disjoint, right? So their sum is 1. And so this is similar to the complement of a set. Right? A complement of a set was just the set of all elements in the universe, so for example, in omega in our case, that are not in A. Right? So it's a similar idea. Any questions so far? Cool. So now, I want you to try and attempt this question. Suppose we have a group of 8 juniors and 5 seniors. What's the probability that a randomly selected group of 4 of these students contains 2 juniors and 2 seniors? Okay? So I'll give you a minute or so to talk with the people near you and try and attempt it, and then we'll proceed. Okay, let's come back together. Okay, so any ideas? What's the probability that a randomly selected group of 4 of these students has 2 juniors and 2 seniors? Let's see. Any ideas? So let's do it one step at a time. What's our denominator, right? Our denominator is all possible ways, the number of ways that we can just select 4 people from a group of 13, right? So our denominator is 13 choose 4. And so now our numerator is the number of ways that in a randomly selected group of 4 of these people, 2 are juniors and 2 are seniors. Is that clear? So can someone tell me what the numerator is? Yep, 8 choose 2, 5 choose 2. Perfect. Okay, what if the question was, what's the probability that a randomly selected group of 4 of these students has at least 2 juniors? How do we approach it then? Well, then it would look something like probability of 2 juniors, 2 seniors, plus the probability of 3 juniors and 1 senior, plus the probability of 4 juniors and no seniors. Right? Then it would look something like 8 choose 2, 5 choose 2, plus 8 choose 3, 5 choose 1, plus 8 choose 4, 5 choose 0, all over 13 choose 4. So this is at least 2 juniors. Is that okay? There's another way we could approach this. We could say it's 1 minus the probability we select less than 2 juniors, right? So 1 minus the probability we select 0 juniors or 1 junior. Sounds good? Cool. And so another thing to remember is the principle of inclusion and exclusion. Right? Remember we said that the cardinality of the union of 2 sets is the sum of the individual cardinalities minus the intersection. Right? We have this picture we've come to know and love. And we can apply this idea to probability as well. Okay, so now suppose A and B are both subsets of omega, then the probability of A union B is just the cardinality of A union B over omega. And we can do a little bit of simplification, and we see that this means that the probability of A union B, so not the cardinality, but the probability, is the sum of the individual probabilities minus the probability of the intersection. So basically, we just tack probabilities on to each one of these terms. Is that okay? So probability with inclusion and exclusion, you'll become very familiar with this. But hopefully you already are somewhat familiar with it because we talked a lot about inclusion and exclusion in this class. Sounds good? Okay, so another question we could ask is, what is the probability that a randomly selected number in the range 1 to 1,000 inclusive is a multiple of 2 or 3? Okay, so I'll give you a minute to try and work it out. Okay. Okay, so what's the probability that a randomly selected number in this range is a multiple of 2 or 3? Well, it's just the number of numbers in this range that are multiples of 2 or 3 divided by the total number of numbers, which is 1,000. So this probability that it's a multiple of 2 or multiple of 3 is the number of multiples of 2 plus the numbers of multiples of 3 divided by 1,000. Is that it? No, right? We have to use the principle of inclusion and exclusion. We have to subtract the overlap because it's counted twice. And in this case, the overlap is the set of numbers that are multiples of 6. Okay, how many numbers are multiples of 2? 500, right? 2, 4, 6, ... until 1,000. How many numbers are multiples of 3? 333. Right, we go from 3, 6, 9, all the way until 999. And how many are multiples of 6? It's 166. We start with 6, and it goes until 166 times 6, which is 996. Okay, which is the biggest one, less than 1,000. And it's whatever that is, divided by 1,000. Is that okay? Sounds good? Cool. We don't have to work out the arithmetic. So now we'll move into this idea of a random variable. Okay? So a random variable is a function that maps an outcome of a random process to a real number. Okay? So it maps some outcome, so the outcome of rolling an even number, or the outcome of picking 4 queens and 5, when I draw 5 cards at a time. Some outcome, so the outcome doesn't necessarily have to be numeric, maps that to some real number. Okay? And so what this notation means, and so this is the probability mass function, okay, of x. What this means is the probability that random variable x, so the big X is the random variable, the little x is the value that it's taking on. Okay? So what f sub big X brackets little x means is the probability that random variable big X takes on the value little x. Okay? And so there's 2 sort of classes of random variables. Okay, the one in most classes that you start talking about first is the set of discrete random variables, and with it come a bunch of discrete distributions. And a discrete random variable is one where the set of outcomes, omega, is a countable set. Okay, so either omega is finite or it's countably infinite. Okay, and those are what we'll look at today. But there are also continuous random variables where the set of outcomes omega is uncountable. So for example, the random variable could take on any real number, for example. Okay? But for now, let's focus on discrete random variables, which have associated with it a probability mass function. Okay? So what we're going to do in the next few slides is look at 2 motivating examples for 2 different discrete distributions in terms of things we already know, and come up with the probability mass functions of both of them. Okay? But before that, a little example. Suppose x represents the outcome of a roll of a dice. In that case, again, omega is just the integers 1 through 6 inclusive. And then the probability that x assumes the value little x is 1/6. Because no matter what the outcome is, the probabilities are all the same, 1/6. But if we want to be a little more explicit, I could say probability x is 1 is the same as the probability x is 2. They're all the same. They're all equal to 1/6. Is that clear? So this notation, when I first saw it, I also thought it was a little weird. You have an equal sign before the actual equal sign. Well, we're talking about the probability of our random variable big X taking on the value little x. Probability that the roll of the dice is equal to this value is one way we can think of it. Is all of this okay? Okay, so let's look at an example. Suppose the probability of me making a free throw, on the court, is 0.6, and assume that each free throw is independent of one another. In reality, that's a pretty bad assumption because I don't think that's true. But for the math, let's hope that it works out. Okay. So whether or not I make the first one has nothing to do with whether or not I make the second one. And so what that means is I can sort of multiply the outcomes for each of the probabilities for each of them, and that works. Okay? And so I want to find the probability that the first shot I make is my 8th shot. Okay, so I want to find the probability that the first success is the 8th trial. Okay? Each free throw represents a trial, every miss is a failure, and every make is a success. Is that okay? So I want to find the probability that the first success is on the 8th trial. Well, if my first success is on the 8th trial, that means I fail 7 times first. Is that clear? And if I make my shot with probability 0.6, so probability p, I miss a shot with probability 1 minus p, right? Because either I make the shot or I miss the shot. So what this means is I miss the first 7 shots. So that means the probability I miss the first is 0.4. The probability I miss the second is 0.4. Probability I miss the third is 0.4, so on and so forth. And I have 0.4 7 times because I missed the first 7 shots. And then that last one I make. That happens with probability 0.6. What that simplifies to is 1 minus p to the exponent 7, because I missed 7 shots, and then my 8th one, I make it. So I have that p. Is this okay? What would the probability that my first make is on my 100th shot be? So first make is shot 100. Well, that would mean I miss it 99 times first, and then make my 100th one. So it would look something like 0.4 to the 99 times 0.6. Is that clear? Are people sort of picking up on the pattern? So in general, this is called a geometric distribution. Okay? Suppose some event succeeds with probability p, and that each trial of the event is independent. Okay? And suppose x is the random variable that describes the number of trials required until the first success. So another example, the number of times I have to flip a coin until it comes up heads. The probability mass function of x is described by this. So the probability that the kth trial is the first success, so the probability that trial k is the first success is 1 minus p to the exponent k minus 1, right? Because the first k minus 1 trials fail, times p. And this makes sense because p is the probability that any one trial is a success. It's the probability that I make the shot. If it takes k tries for me to make my first shot, well, that means the first k minus 1 times I didn't make the shot, and then the kth trial, I make the shot. So we have 1 minus p multiplied by itself, k minus 1 times, and then times p at the end. Does this sort of make sense? So any questions with the idea of a geometric distribution? Okay, and there are a bunch of other properties of distributions that I'm intentionally not talking about right now because they're not that relevant. But this wasn't that hard to pick up from when we look at it as a counting question. This is really just a counting question. We're multiplying ways to do things, and that's something we're comfortable with right now. Is this okay? Cool, so this is what's called the geometric distribution. But now for something a little more directly relevant to what we studied. Okay? So now, before with the geometric distribution, I was thinking about how many times do I have to shoot a basketball until it goes in, right? Now, I want to think of if I shoot it 100 times, and each shot goes in with probability p, how many times is it going to go in? Right? Or if I flip a coin that's biased with probability 0.6, so it comes up heads with probability 0.6, tails with probability 0.4. If I flip it 5 times, how many times will it come up heads? So now this is the question I want to ask. Okay? And so we know each of our 5 flips could either be a success or a failure. In this case, we're looking at heads or tails. And so what we want to do is figure out how many ways can we permute, or like how many of these possible outcomes have exactly 3 heads. Okay, so really what we're doing is we have the characters H, 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 T, and T, and we want to find all permutations of it. How many permutations of this are there? Is that clear? Because all permutations of this would tell us all possible orders in which we could get 3 heads and 2 tails. Is that clear? And the question is, how many permutations of this are there? Well, there's 5 characters. Divide out by the repeats for the heads and the tails. 3 repeating heads, 2 repeating tails. Well, that's really just the same thing. As we have 5 characters, or 5 flips, choose 3 of them to be heads. Similarly, if I'm shooting the basketball 100 times, and I make 60 of them, let's say, the number of ways I could do that is 100, choose 60. Is that okay? Cool. And now, for each of these sequences of 3 heads and 2 tails, each head occurs with probability p, and each tail occurs with probability 1 minus p. And since we're assuming all of these coin flips are independent, we can just multiply all of these probabilities together. So if I get 3 heads and 2 tails, the probability of that happening is p cubed times 1 minus p squared. So this corresponds to, this should be a 3. So these correspond to 3 heads, and these correspond to 2 tails. And that's for every combination, or every arrangement of 3 heads and 2 tails. But we can do this 5 choose 3 ways. So we have to multiply this probability by 5 choose 3, because I have to account for every possible arrangement. Okay? So what I can say is that the probability that I get 3 heads is equal to 5 choose 3 p cubed 1 minus p squared. We can be even a little more specific. In this case, p is 0.6. 1 minus p is 0.4. So this is the probability of making exactly 3 of the shots. In any one specific arrangement, I'm sort of interchanging the shots and the heads, but hopefully the analogy is clear. A success is the heads, a failure is the tails. And any combination or any arrangement of 5 flips, the probability of 3 of them being heads, 2 of them being tails, is 0.6 cubed times 0.4 squared. But then we have to account for the number of ways that could happen. Right? And so we have 5 choose 3, 0.6 cubed, 0.4 squared. Any questions with this? And so this looks similar to something we've seen, right? And this is actually called the binomial distribution. Okay? So suppose an event succeeds with probability p, and each trial of the event is independent. Okay, so we're assuming that each coin flip is independent, each shot at the free throw line is independent. I think I spelled independent wrong. Okay, and suppose x is the random variable that describes the number of successes in n trials. Then the probability of k successes is n choose k, p to the k, 1 minus p to the n minus k. So this looks very similar to something you've seen. Well, that's because it's a direct application of the binomial theorem. Okay? Specifically, this is the general term in the expansion of p plus 1 minus p to the n. It's the general term of that expansion. Okay? So, general term of that thing. Okay? So not only did we talk about the general term just for fun, but it also has direct applications to things you'll see in the future. Any questions with this idea? Okay? Both of the distributions we've looked at, as I mentioned, are discrete. Here, with the binomial distribution, there are n plus 1 possible outcomes, right? There are n plus 1 terms in the expansion of something to the n, right? I could either, like if I'm flipping the coin 10 times, it could either be heads 0 times, 1 time, 2 times, so on and so forth until 10 times, right? So if we're using a fixed number of trials n, the total number of possible outcomes is n plus 1. So number of possible outcomes is n plus 1. Is that good? How many possible outcomes were there with the geometric distribution? How many possible outcomes are there? So it's not k. K is a placeholder variable for that specific number you're evaluating. But how many different k's are there, I guess is what I'm asking. So here, there are only n plus 1 different k's. Suppose n is 5. I can't ask for the probability that I made 7 of my shots when I only took 5 shots, right? If n is 10, if I flip the coin 10 times, it doesn't make sense to ask, what's the probability that I flipped 11 of them? Or 11 of them are heads. That just doesn't make sense. Similarly, it doesn't make sense for any of those to be negative. Right? Although outcomes can be negative, probabilities can't, of course. Right? Over here, I'm talking about how many times do I have to shoot the shot until I make one? And the answer is there's infinitely many options. It's possible that I shoot it 1,000,000 times and I still don't make it. It's very, very unlikely, but it's possible. Right? Similarly, I could sit there flipping a coin. Within the first couple flips, it'll probably be both heads and tails. But nothing's for certain. Right? I could sit there flipping it 10 trillion times and it could still potentially not be heads. Right? So how many possible outcomes are there? Infinitely many. But this is still a discrete distribution, and that's because the set of outcomes are just the natural numbers, right? It might take 1 attempt until I get my first success, 2 attempts, 3 attempts, 100 attempts, 10,000 attempts, whatever. That's just the set of possible outcomes is the set of natural numbers, and that's countable. So it's still a discrete distribution. So still discrete. Is that okay? So there's infinitely many possible outcomes, but it's still a discrete distribution. Here, there's only a finite number of possible outcomes. This okay? Cool. And so now, I wanted to talk about the birthday paradox, which is what I asked in the quiz attendance form. And so the question you want to talk about is, we know there's 365 unique days in a year, 366 with leap days, whatever. What's the probability that in a group of n people, at least 2 people share a birthday? Okay? That's what we want to investigate. What's the probability that in a group of n people, at least 2 share a birthday? Okay? So one thing to note is that if we're looking at a group of more than 365 people, what is this probability equal to? If we have more than 365 people, it's required that at least 2 share a birthday. Because there's only 365 different birthdays. So that means if we have more than that many people, at least 2 have to share the same birthday. Right? It's like, for example, if you look at a group of more than 4 undergrads, you'll have at least 2 freshmen, or at least 2 sophomores, or at least 2 juniors, or at least 2 seniors. They can't all be a different class standing if there's at least 5 of them. Right? Because there's only 4 different labels you can assign to them. And that idea is called the pigeonhole principle. Okay, which we briefly touched upon this semester. But let's look at the case where we have less than 365 people. Okay, so if n is greater than 365, the probability is 1, but that's not the important case. So what if we have a smaller group? The insight we need to make is that there are 2 disjoint cases that we can look at. Either nobody shares a birthday, so everyone's birthday is unique, or at least 2 people share a birthday. Okay? These 2 things are disjoint. One of them always happens, right? One is the complement of another. So the sum of their probabilities is 1. And so the one we care about is the probability that at least 2 people share a birthday. On the left-hand side, this is what we want to look at for different group sizes. And what I'll call that is P of n. Okay, so essentially what I want to do is find some way to determine a function of n that gives me the probability that at least 2 people share a birthday in a group of that size. Okay, and what we're building up to is we'll come up with the function and then plot it and see at what point is it more likely than not that 2 people share a birthday. Okay? So let's take a look. And this is sort of the notation for what we're looking at. P of n is what we're trying to find. And what we'll say is that this is 1 minus the probability that in a group of size little n, everyone has a unique birthday. Right? And this is, again, a technique you'll see pretty often. If you can't find something directly, it's often easier to look at its complement and find the probability of its complement. Okay? And so what the assumption here is that it's easier to find the probability that everyone has a unique birthday. And so that's what I want you to do. Consider the two-person case. What's the probability in a group of two people? At least two people share a birthday. And so what you should start by doing is find the complement of this. So instead, first find the probability that all birthdays are unique in a group of size 2. Okay? So do the opposite of what the text is asking you. Figure out, in a group of two people, what's the probability that everyone has a unique birthday. I'll let you discuss it for a couple minutes. And then see if you can generalize it to a group of n people. What's the probability that a group of n people all have different birthdays? Okay, so again, as I mentioned, first we want to find the probability that in a group of two people, both birthdays are unique. And then to find the probability that at least two people share a birthday, it's 1 minus that. So what's the probability that in a group of two people, nobody shares a birthday? Anyone able to figure it out? Yeah. 365 times what?
So like any of the first person can have any of the days, and the second person can have any of the days except for that one.
Right, but this is not a probability.
Oh, it's like divided by.
Yeah. So it turns out that it's this divided by 365 squared. So let's look at it one person at a time. So we have two people. What's the probability that the first person has a unique birthday? We're just looking at the first person. 1. Like we haven't seen any birthdays, their birthday is unique. So it's 1, but we'll write it as 365 over 365 for reasons that'll be clear pretty soon. Then, now let's look at the second person. What's the probability that their birthday is unique? 364 over 365. They could have any birthday other than whatever the birthday of the first person was. Over 365. If we were instead looking at the case with 5 people, what's the probability that all 5 of their birthdays were unique? Well, we would just continue multiplying this by 363, 362, and 361, all over 365, 365, 365. Is that clear? So the probability that we found is the probability that in that group size, we've used 5, but let's go back to the example of 2. All birthdays were unique. So that means the probability we're looking for is that people share a birthday, right? And so the probability that at least 2 people share a birthday in a group of size 2 is 1 minus this probability. which is actually pretty small in this case. It's 1 over 365, which makes sense in the two-person case. Pretty small. You pick two random people, the chance that they share a birthday, not that great. But you'll see, when you extend this to a general n, the number of people that you need such that you have a probability of at least 50% of two people sharing a birthday is pretty small. Okay? Let's generalize this to the n-person case. Okay? So just extending the pattern we saw on the previous slide, the probability that in a group of little n people, everyone has a unique birthday, we just start with 365 over 365, and just keep dropping the numerator while keeping the denominator the same. Right? Remember in the n is 2 case, we had 365 over 365 times 364 over 365. In the general n case, we multiply the numerator until we get to 365 minus n minus 1. Right? To see why that works, 365 minus 2 minus 1 is 364. So it generalizes the pattern we just saw. But this is really just the number of ways you can permute from a group of 365 elements, n of them. Right? It's just like saying, if I have 365 people, how many ways can I arrange n of them in a line? But now instead of people, we're thinking about birthdays. How many ways can I, from a group of 365 people, can I arrange n different birthdays? Okay? But just as an aside, remember that the number of permutations of k objects from a group of n was just n factorial over n minus k factorial. So to put it in terms of things we know, you could say that this is n choose k times k factorial. Because n choose k has the added k factorial on the denominator, so we multiply by k factorial outside to account for that. So what we can say then is that the probability in a group of little n people that all birthdays are unique is 365 choose n times n factorial divided by 365 to the exponent n. And this is just a generalization of what we just looked at over here. If you plug in n is equal to 2 in what I just highlighted, you'll get back this result over here. Is this okay? And so, remember, we don't want the probability that everyone has a unique birthday. We want the probability that at least 2 people share a birthday. And so it's 1 minus what I've highlighted. So this was the end result we were looking for. The probability that in a group of little n people, at least 2 people share a birthday is 1 minus 365 choose n times n factorial divided by 365 to the n. Does this sound okay? Okay. So for the people who haven't seen this before, if you have seen it before, don't guess because you know the answer. What is your guess as to how many people you need in order for the probability that at least 2 people share a birthday is greater than 50%? What's your guess? Any ideas? Someone please guess. Sure, I heard 100. What about you? 365. Half of 365. Okay, so our guess is in the 100 to 180 range. Of the number, that's the guess of the number of people we'll need, such that the probability that 2 people share a birthday is greater than 50%. How many people know the true answer? Don't say it if you do, but how many people know? A few. Okay. Don't laugh at the people who guessed. You might soon though, but we'll see. Okay, so let's do some calculations. Okay, so Data Hub never works. Okay, import matplotlib.pyplot, PLT, matplotlib inline. Okay, so what we're going to do is implement the probability function we just saw, right, and plot it for various n, and we'll also draw the line at 0.5 and see the value of n that causes the probability to go above 0.5 and see where it lands. Okay, so first, to implement this, we need both a factorial function and a choosing function. Okay, and let's suppose we don't know what numpy is, so we have to sort of do these from scratch. So first we have to import, what am I doing? Define factorial. And what I can say, if n is less than or equal to 1, return 1. Otherwise, return n times factorial of n minus 1. Pretty standard, right? Now I also want a choose function. Oops. And how do I implement this? Well, I want the factorial of n divided by the factorial of n minus k times the factorial of k. Is that clear? N factorial over k factorial, n minus k factorial. Now we can define our probability that two people share a birthday. And what was it? Well, it was 1 minus, now going back to this slide, 1 minus 365 choose n times n factorial over 365 to the exponent n. So we have 1 minus 365 choose n times the factorial of n divided by 365 to the exponent n. Sound good? Okay, and so now what I'm going to do is, let's just say upper limit is equal to, what was our guess? 365 over 2. So let's just say 200, okay? What I'm going to do is plot this function for n is equal to 1 to n is equal to 200. Is that okay? So what do we need? Well, we need range 1 to upper limit plus 1. You can say y is prob shared of xi for xi and x. Okay? So now I need to plot x and y. But I also want to plot the line at 0.5. Okay, so how does plt.plot work? You specify the list of x's and the list of y's. So where the x is going to be 1 and upper limit. What are the y's going to be? 0.5 and 0.5. So when I run this, it should give me the plot I'm looking for, and the line, the horizontal line, will be at y is equal to 0.5. So let's take a look. Yay. In too large to convert to float. Don't you love Python? Too large. Okay. Why don't we start with 100? There we go. So, the orange line is the line where the probability that at least two people share a birthday is 50%. And so where does this curve cross the orange line? Around 23, which is actually the number of people that you need such that on average two people share the same birthday. Isn't that crazy? So why don't we look at some of the values in that range? So for I in range 130, print I, comma, prob shared by. Cool. So this is, for various group sizes, the probability that at least two people share a birthday in that group size. And you can see, at 23, the probability becomes greater than 50%. Right? So significantly smaller than the guesses of half of 365 or even 100. Isn't that pretty cool? Any questions with all of this? Cool. So I think that's all we have for the semester. So some closing remarks. Hopefully what we did today showed you that while we didn't cover everything that you'll learn in mathematics, we gave you a pretty good foundation so that when you go out and learn new things in whatever classes you take in the future, hopefully a lot of it can build upon the stuff you saw this semester. Okay, so I think that's it pretty much. I'll stay around if you have any questions. I'll also put up the attendance link, and you'll get an email tomorrow or Saturday talking about the grading rate. But that's it.